In the previous section, we looked at questions about the existence of solutions of linear systems. This led us to the concept of the span of a set of vectors. In particular, when we talk about the span of a set of vectors v1, v2 through vn, we're talking about the set of vectors B for which the system ax equals b has a solution. And in particular here, we are talking about the matrix A consisting of the columns that are the vectors, v1, v2 through vn. So if we have this matrix A with columns v1 through vn, and that system ax equals b, or that equation ax equals b, has a solution, we say that any vectors that are solutions of that equation are in the span of the set of vectors. Said another way, the span of a set of vectors is the set of all linear combinations of those vectors v1 through vn. In this section, we're going to look at the uniqueness of these solutions. So not just does a solution exist, but is that solution unique? So let's take a look at a couple of examples. To begin with, let's consider the vectors v1, v2, and v3 shown here. So v1 is 1, 2, 1, v2 is 3, negative 1, 0, v3 is negative 1, 5, 2. We want to describe the span of these vectors, and we showed in a previous section the one way we can do that is by setting up this matrix whose columns are given by these vectors, and we're going to augment this with sort of uh, a general vector x, y, z to see sort of what vectors of the form x, y, z can we actually get to by taking linear combinations of our vectors. Said another way, these vectors x, y, z are going to represent sort of those solutions b to that equation ax equals b. And so we can set this up and we want to row reduce now. So let's row reduce this. We can do an R2 minus a 2R1 and an R3 minus an R1, 1, 3, negative 1, x, and then 2 minus 2 is 0, negative 1 minus 6 is negative 7, 5 plus 2 is positive 7, and then we're going to have a y minus 2x. And then 1 minus 1 is 0. 0 minus 3 is negative 2. 2 plus, negative 3. 2 plus 1 is 3. And then we're going to have a z minus x. We can now scale row 2 by dividing it by a negative 7. Get a 1 in that pivot. So 1, 3, negative 1, x, 0, 1, negative 1. And then this is going to be a y minus 2x divided by negative 7. Third row stays the same. And now we can do an R3 plus a 3R2. And what we're going to see is that we're going to get that third row as all zeros. And so this is going to help us describe that span. So we get, 0, then negative 3 plus 3 is 0, and this is going to be a 3 minus 3. So that'll also be a 0. And then our last column becomes z minus x, and then plus 3 times this y minus 2x over negative 7. And so what we've discovered here is that the vectors in the span of the form xyz must satisfy the equation to make this third row and in this last column equal 0. Otherwise, this system would be inconsistent. So we know that for all of our solutions, z minus x plus, maybe we'll write this as a minus 3/7 times y minus 2x needs to equal 0. And I just want to clean this up a bit. Maybe I will, multiply everything by 7 just to get rid of that fraction and then distribute that minus 3. So we'll have a 7z minus a 7x, and then minus a 3y plus a 6x. That equals 0. And then just sort of combining like terms and rearranging things, we can get a negative x, negative 7x plus 6x, and then a minus 3y, and then a plus 7z equals 0. And we've seen this before in previous sections. This is the equation of a plane. So all points x, y, z that satisfy this equation will give us a plane in 3 dimensions. We're going to look at that geometrically relatively soon. So one thing we know here is that actually infinitely many vectors are in the span of these 3 given vectors, right? Any vectors that lie on this plane given by this last equation, negative x minus 3y plus 7z, are going to satisfy that system and therefore be in the span of these 3 vectors. So we might say here that these vectors span this plane. What you can see here is the same 3 vectors, but a slightly different question here. So we have v1, v2, and v3 as we had before, but instead of asking for their span, we're asking to show that v3 is a linear combination of the other 2 vectors. So if we sort of, we're trying to answer this question, what we could do is set up this augmented matrix where we've got v1 and v2 as the columns of that sort of coefficient matrix portion. And we could have v3 as the right-hand side, and we could kind of row reduce. Now, if we go back to the steps we did in the previous slide, what you would see is that, if we were to kind of go through this process of row reducing, the final matrix we would get would essentially just be what we have down here. The fact that we're moving that vertical line left or right is not going to change any of the actual operations that we did to row reduce this matrix. And the last column being worked through like we did in this example, eliminating that is not going to change sort of what's going to happen in the other columns. So one of the beauties of doing elementary row operations is that we are really only affecting what's happening in these rows and not necessarily what's happening kind of column by column. In other words, we can eliminate a column or multiple columns and perform the same elementary row operations on the remaining matrix, and we're going to end up with whatever we would if we had left those columns in, but just sort of removing those columns. So if we go through the process, we're going to get this 1 3 negative 1 0 1 negative 1 0 0 0 matrix after we go through that row reduction process. So this will row reduce, and you're certainly welcome and encouraged to try this to just double check that it does work. But again, we're going to get sort of that 1 3 negative 1 0 1 negative 1 0 0 0 matrix. We can put that vertical line there just to be consistent with our current problem, but nothing else is affected. And so what this tells us is that if we call sort of the coefficients here C1 and C2, this matrix does show us that we have a solution, and we can see that if we multiply, so we might want to actually do one more step of our reduction because we're not in reducer echelon form yet. So let's actually go ahead and do that. So we could do R1 minus 3R2. We didn't need to do that before just because, we weren't trying to get this far, but here we can go 1, and then 3 minus 3 is 0, negative 1 plus 3 is 2. All right. And then 0, 0, 0. So we do have solutions, and what we can see is that C1 would equal 1, or excuse me, C1 would equal 2, C2 would equal negative 1. So this tells us that 2v1 minus v2 should equal v3. And so in this case, we would say that this set of vectors is linearly dependent. We're going to define that in another video soon, but the concept that we're getting at here is linear dependence. And if we go back here, we sort of saw that the span of these vectors is this infinite set. And so this concept of linear dependence is potentially somehow related to that span being an infinite set. And we're going to try and make some of those connections a little bit later. Let's look at one more example of a different set of vectors, u1, u2, and u3. We're back to the question of just describing the span. So if we set this up, these are different vectors now. And we augment that with a sort of like XYZ vector there to describe the span. And we could go through the whole process of row reduction and sort of seeing what happens to our matrix. I will say, if we go through that process, I'm not going to go through all the steps, that coefficient matrix side would row reduce to this matrix here, 1, 0, 0, 0, 1, 0, 0, 0, 1. We've called that the identity matrix in a previous video, so the 3 by 3 identity matrix. And then over on the right of this vertical line, we're going to get sort of some combination of, X, Y, and Z in each of these rows. And if we wanted to figure out specifically what those combinations look like, we would have to go through the row reduction steps. But actually, I don't really care what those look like if all I care about is describing the span of these vectors, because the fact that we got this 3 by 3 identity matrix over here basically tells me that, I'm not going to be in a situation where I need to require one of my rows to equal 0 on the right-hand side, because I don't have a row of zeros in that coefficient matrix portion like I did earlier. That essentially tells me that the span of these vectors is going to be everything in R3. And so, again, if I wanted to get a specific vector in R3, I would go through the process of putting that particular vector in for XYZ and row reducing. It's not worth kind of doing this in general when we know we can get to every vector. And so we would say that the span of these vectors is all of R3. Let's look at some geometry here. I've got some images of these two different examples. The first example, which were these set of vectors v1, v2, and v3, which we said just span that plane, and so we can see the plane there. And then those other vectors spanning all of R3. It's a little bit hard to kind of see what's going on here. So I want to go to actually this website where I can kind of do this rotation, and you can see. So these are those first three vectors. And I'm claiming they're sort of lying on that plane. And you can see as I rotate this, hopefully it becomes a little bit clearer. We can kind of look below and above. It becomes clear that yes, indeed, those three vectors are all lying on the same plane. So their span is just that plane. Another thing we can kind of tell from this, hopefully, is that V3 is in fact a linear combination of V1 and V2. We can, kind of scale each one of those in specific ways and add them together in a way to get to V3. If we go to those other vectors, U1, U2, and U3, then, kind of do some of that rotating, you can see that those span all of R3. They do not all lie in the same plane. They're sort of pointing off in different directions. Show you a bunch of different angles here so you can hopefully get a feel for this. The website I'm using here, by the way, is called CalcPlot3D. It's got a lot of tools. There's a bit of a learning curve to figure out how to sort of make it look nice, but there's a lot of tools to put vectors in. You can come up here to this Add to Graph menu, and if you click on that, you can add a vector there. All right, so on to now the main topic of this section, which is linear dependence and independence. So we say that a set of vectors is linearly dependent if one of the vectors is a linear combination of the others. Otherwise, the set of vectors is called linearly independent. And so questions about uniqueness of solutions will lead us to the concept of linear independence. We started to explore that already with these examples. If we go back to our examples up here, then we would say that V1, V2, and V3 are linearly dependent because we can write V3 as a linear combination of V1 and V2. So we have the fact that this set, maybe I'll write it using set notation, V1, V2, V3, this set of vectors is linearly dependent. If we compare that to U1, U2, and U3, um, if we were to sort of play our game of trying to, I didn't ask this question, but if we were to try to write U3, let's say, as a linear combination of U1 and U2, so put our vertical line here, this would reduce to the matrix, same sort of identity matrix here, this vertical line here, we could see that this last row is, that kind of row that tells us that this system is inconsistent. This is our 0 equals 1 row. So we know that that is not possible. And so since we cannot write U3 as a linear combination of U1 and U2, and we would not be able to write any of these as linear combinations of the others, we would say that this set, U1, U2, U3, is linearly independent. Okay, and we're going to connect this in a little bit to the concept of uniqueness of solutions, and so we'll see sort of what that means in a future video.